Great. So, firstly, this is a checkpoint lecture. This is our seventh lecture since the beginning of the reading group. I would like firstly to remind ourselves of the plan that we initially had for our reading group, which was to provide college quality, university quality reading group for art and algebra while finishing the whole curriculum of the book without skipping sections and so. But due to the flow of our past lectures, it happened that we had to skip some lectures, some sections, not lectures, sorry. So before we start and get to the plan of what we're doing today, I would like to share my screen and tell you where we are in the in the course. Firstly, this is the content of our book. It's the first edition, not the second edition. It's I want uh, yeah, it's the 1991 edition. The content, the first thing that we skipped was chapter one. It seems that like a counterintuitive thing to skip, but like we are assuming that that anyone here has a pretty good background on linear algebra, even at the computational level. And then we took groups. We studied isomorphisms, equivalence classes, cosets, and products of a group, quotient groups, and we even have a section on modular arithmetic. We didn't skip any part here. Now, then we got to chapter 3, vector spaces, and chapter 3 and chapter 4 is like kind of a break from the group series that we had before, and was a kind of a jump into abstract linear algebra. In chapter 3, we skipped sections 2, 5, and 6. Section 2 was on abstract field. The presenter of that part felt that it's okay that we skip the introduction, if you call it, of abstract fields, as as we see, we will discuss fields and Galois theory in the end of our reading group. Yeah, actually, that would be the absolute end of the reading. Now, we also skipped in chapter 3, we skipped section 5, infinite dimensional spaces, and chapter 6, directed sums. Like, generally, they don't get um, mentioned a lot and will not get mentioned a lot, but I feel that we also need to go through them for a bit. Then we started linear transformations. We skipped the pen center. I hope he hears me. If you do, hi pen center. I'm not in the script now. The first section was the dimension formula. I think it was reasonable to skip for our for the prerequisites that we assumed in the beginning of the group, but we may go for it again due to like I see that the proofs is, are fun to go through, and then the kind of big section 4.5 orthogonal matrices and rotations. And then the last thing that we are going to discuss today will be sections 4.7 and 4.8 if you had time. We didn't skip those. It was planned to go through either way, but like it's a beginning. It's a new topic that we didn't actually get to explain in the last lecture. So if we had time after that, we will um, we will have sections 4.7 4.8, and our break would actually be around here because I don't I section 4.5 actually like kind of three sections combined. So before I start, anyone has any questions at all?
I'm not seeing any so far in Discord, but feel free to keep typing if you're.
Great. So uh, the first thing that we are going to discuss today is abstract fields. We studied before. I think Red was the presenter in Red and Goose. I think was the presenters of chapter 3. We studied vector spaces over the real numbers um, and complex numbers. We didn't get too far in the complex linear algebra, but I think we know what I'm discussing. So the book actually starts by defining what is a field. It starts with giving examples of fields. We see that the provisional definition for fields. I want to write this verbatim. Yeah, one second. Yeah, provisional definition of a field was that a subfield of or a field is kind of a field is a subfield of the complex numbers with five axioms. The first axiom that one is in the field. In the main definition, we will see that the zero is also in the field, and we'll discuss this more, like why he didn't explicitly say that here. And closure under multiplication under addition a and b in f, then a plus b is in f. 3a and b is in f. Then a multiplied by b is an f. And then we see that there's an additive for every a. There is negative a in the field. And lastly, for every a doesn't equal to 0, there is 8 power of minus 1 in the field. Now, it's not mentioned here that, like, for example, we can say, yeah, we can say that we can add another axiom that 0 is in the field. It's not mentioned here. because from the axioms of closure under addition, and from the axioms that there is an additive inverse, and from the axioms that there exists one, we kind of deduct that zero exists, the zero element exists, and also there are some inherited structure from the complex number that the stating of the zero is a distinct element in the field kind of feel redundant. But there's actually some fields that we will discuss known as abstract fields or prime fields that we need actually to say that one and zero are distinct fields. For example, if I actually talk about the actual definition, and I just want to give you the idea between the professional definition and the actual definition, because the professional definition is the one that gives you the intuition for the subject. You see, a uh, field F is as set together with addition and multiplication. It's like two laws of composition, so on and so forth. I don't need to state that explicitly. All the addition and satisfying the following axioms. One, addition makes F the field an abelian group, and the identity element for it is denoted zero. Let's underline that part. Two, multiplication makes F without the element zero an abelian group. Two. And the identity element for it is denoted one. You see, the definition says that the identity element for addition and is denoted by zero or as denoted by e simple, and multiplication the identity is denoted by a different symbol. I will state the third axiom. The third axiom is just distributive laws. Laws. I don't have to explicitly write it, but like the important part that it the identity element for addition and the identity element for multiplication are both denoted separately. So let's let's for example try something. What is what is the easiest or the smallest field that I can make from these axioms? The answer would be the field equals 0 and 1. Now, now the definition says there's multiplication and addition, so I must firstly let's check that the addition the table holds. So here's addition 0, 1, 0. From our numbers easy 0 plus 0 is it's zero is the identity element, so 0, 1 and 1. Now 1 plus 1 here must be equal to 0. Why? Because if for example I just want to add that counter example, if counter example, if 1 plus 1 were to equal 1, then 1 would be the identity. 1 would be equal to 0. That's the important part of denoting the identity elements in different symbols or different ways. Uh, and multiplication is easy. We have 0, 1, 0, 1. 0 times anything is 0, and 1 times 1 is 1. That's easy. Now, the question here for the audience, this structure, what do you see that it is isomorphic to? It's or maybe not isomorphic, it's like a structure that we already know. Yeah, I'm waiting for answers. The permutation group of two items. Uh, yes, that's isomorphic to it, but like I want another answer, specific answer. I can't hear that, but like I'm open to the chat, if anyone. Yeah, yeah. The question is the structure, the break structure of this field with addition and multiplication stated like this. We saw the structure before. The structure is isomorphic, as Kirby said, is isomorphic to the permutation group of two items or two elements or two letters. But we've seen this structure before. Like it's not even isomorphic structure. This structure we saw it before. Mm, that's not actually. That's the answer is easier than that. Like when you see if no one can say the answer is easy than anyone of you thought. It's actually 3 mod 2. Like if you are adding, we know that 0 in z mod 2 is is equivalent to even numbers, and one is equivalent to odd numbers. Even plus even is even. Even plus odd is odd. Even plus odd is odd. Odd plus odd uh, is even. Multiplication also, even times even is even. Odd times even is even. Odd times even is even, and odd times odd is odd. Yeah, it's easier than the answer any one of you saw. So yeah, it's not even it's not even isomorphic. Like Kirby, the best answers that I got was from Kirby. The permutation group of two letters that's actually isomorphic, but this structure doesn't need to be isomorphic. It is the structure of Z modulo 2. Now we have actually a kind of kind of important detail to notice that 2 here is a prime number. What if, like, we will prove that, but like, I want to do something. What if, for example, I made the theme mod 6, Z modulo 6? Would it be a field? Let's see. Uh, we will say F dagger, I don't know, and that kind of simple. I just want to some. So is equal to 0, 1, 2, 3, 4, 5, and equal to Z mod 6G. Let's look at the axioms that we had. Red, I saw the question. What do you mean by that? I saw these were different structures still, but isomorphic. The field, I am saying that the structure of Z modulo 2 is actually is the structure itself. It's like is a field, not it is a field. That I'm saying this is a field, and any other, and I'm saying now I'm trying the the permutation group of two letters is isomorphic to that group. So they are isomorphic. Now here I'm trying to say, what if the field was Z modulo 6, for example? We'll make a field. We say we have the addition is defined. We have multiplication is defined, and we have the zero element and distinct one element, and we will see that the distributive law holds. Yeah, yeah. The model 2 is an example of a field, yes. But the problem here is with inverses. You see, um, for multiplication, we know that a modulo 6 times b modulo 6 equals ab modulo 6, like together. We saw that in our group series stuff. Now Let's let's take 5 for example. What is the inverse b that I can multiply by to get 1? Is this even possible to do? Let's actually uh, like hardball it. Let's like try to do it. What is then 5 times p would be actually m times 6 plus 1. Um, mm, we can I I don't see any element that can do that. Like if we, for example, 5 times 4 module, then it would be 20, which is yeah, which is 2. Yeah. Then 5 times 3, it's 15, which is 3, I think. Yeah. 5 times 2, 10, which is 4. 5 times 1 is 5. 5 times 0 is just 0. I don't see any way that there is a multiplicative inverse for the element 5 in Z mod Z, Z mod 6. We can say that the inverses here 5 no 5 times 5. It's not its own inverse. It's 25. 25. Yeah, wait. Maybe it's all. It's all. Yeah. Yeah. Wait. Its own inverse. Oh. Yeah. Then then I made a bad example, but like there's an element here. I don't know. Some element here, maybe 4, maybe 3. I didn't actually hard do it. But you won't find an inverse for every element here. Uh, just to note, 0 doesn't count because the, the multiplication makes f minus 0 an abelian group. So if you add 0, we won't be able to find an inverse for 0 anyway. So now, as Red mentioned, you don't think 4 has an inverse? Yeah, maybe. Let's try it actually. 4. 4. Wait, wait. Yeah. 4 times 0 is 0.
I think
4.
3 would be easier to check because it's half of the mod numbers, so multiplying it by anything will either be 3 or 0.
Yeah. Yeah, but we already started 3 and 4. We will just it's and the sixth operation is still so 4 is 4 and 4 times 2 is 2. 4 times 3 is 0. I think, yes. Yeah. 4 times 4 is 4. not zeros. I think 4 times 4 is 16, and yeah, 4. 4 times 5 we saw it to be 2. 4 has no inverse in the mod 6, not mod 7, mod 6. For example, let's check 3 times. It's still same stuff, so it will be yeah, 0. 3 times 1 is 3. 3 times 2 is 0. 3 times 3 is 3. 3 times 4 is 0. 3 times 5, we saw that to be 3. We can do the same with 2 and with and even with 1. Maybe we saw I picked a wrong example for 5, but like most elements here won't have an inverse, excluding 0, of course. This breaks the second axiom that that makes if minus the element 0 an abelian group. Okay, and why Z mod 2 was a special case? Why did it make a field despite despite Z mod 6 didn't make a field? The key here that 2 is a prime number. Now we will say that we saw in the Benedict Gross lecture the let's actually try to make the proof. I just want to see, yeah. Mm, yeah. To prove that any Z mod B Z mod BZ is a field. Yeah, in fact, I further predict that any composite mod isn't a field because any multiple of will cycle between its own multiple and 0. Yeah, that's actually a good note, but like we firstly want to prove that even Z mod B is a field. We would have uh, to do that. I will show that if we do that by if, make an element A. Looks right, right. Make an element A that it's not congruent to 0. Mod B, of course. Then there's an integer A times P equals. How will we do that? We can do that by the geometric, the Euclidean algorithm, but like Professor Benedict Gross made it in a nice way with isomorphisms theorem. We say that Z mod PV is actually a maximal a maximal subgroup of Z. Then if A is not wait, sorry, B BZ is a maximal subgroup of Z, not ZVZ. BZ is a maximal subgroup of Z. Then as A is not congruent to 0, then A is not in BZ. Then BZ plus AZ is Z. Why? Because BZ is a maximal subgroup of Z. So if you did something higher than BZ, then it actually is a group in the integer groups at all. So
Hey, Mohammed, you're getting a
so
little bit out of frame. If you could, yep, that direction.
yeah. Uh, so then uh, we know that one is 1 second. Uh, well, yeah. Uh, am I in frame now? Uh,
Not quite. We can't see of Z, presumably.
you can see it now.
I can see it now.
Yeah. Uh, we know that Z is in Z. One is in Z. So one is in Z. Then one is equal to some multiple of P plus BA. Then one is actually BA mod C. That so for any number that in Z mod BZ, we see that any element in that group or in that field, any element must have an inverse. This is for the fact that P is a prime number. We can't do that. We can't do that trick here of that trick here of the Euclidean algorithm and the trick of the isomorphism if B was a composite number. Actually, as an introduction to what we will cover later in the course, Galois proved that any field, um, any field has the order of P n for any P and n in greater than or equal. Yeah. Now we see that actually. Let's get to our provisional definition. We see that a field is a subfield of the complex numbers. And we talked about how we didn't mention zero and this stuff. Z mod be the subfield of the complex numbers? The answer is no, because as we know that we talked before about the cyclic groups and we talked about how the cyclic groups are isomorphic to Z mod n, and so we know that I have to cycle back. I have to cycle back in addition. So in multiplication even. So like in if in complex numbers in C, we find that like if 1 plus 1 plus dot plus 1 n times equals n, but like in Z mod BC, we see that 1 plus 1 plus dot p times is equal to 0. We cycle back. We didn't do that in our subfields of complex numbers. So before I define vector fields in on vector spaces on abstract fields, I just want to let us ponder on the two definition of fields that we made. Professional definition, the one that gives us the intuition actually, the subfield field is a subfield of C, or even a field is a subset also of C. Uh, we didn't explicitly state that the distributive laws hold because it inherits that from its parent field, the complex number. We we actually stated that it's a closed under addition, closed under multiplication, and for every a there's an additive inverse, and for every a doesn't equal to 0, there's a multiplicative inverse, which all actually coincide with the definition that we or the actual definition for a field that we have. The main difference between the two is the difference that the difference is that every sub every subfield of C that satisfies these conditions are a field, and actually are a field that we can imagine and we can have the intuition for, but like not every field is a subfield of the complex numbers. Are there other any questions on the topic of abstract field? I will now start defining abstract vector spaces. I don't see I don't see any questions. So let's start defining our abstract vector space. Yes. Vector space. Let's see first. Oh, wait. That's not enough. 1 second. And a second, my stuff got mixed. So yeah, 1 second. We're back. Abstract a vector space. Actually, the definition of a abstract vector space is one of the most definitions that I like. An abstract vector space over a field F is a set together with two laws of composition. One. Let's start. Uh, uh, I don't want to define it explicitly, but like vector addition and scalar multiplication. The scalars come from the field here. Yeah, yeah, you can see that right now. And satisfying the following axioms. Addition addition makes V into a commutative group. 9. Addition makes V into a commutative group. Yeah, you can see that now. And scalar multiplication is associative with scalar multiplication is associative the element one acts as the identity one dot v equals v, and this lastly this distributive flows. Oh, that's the definition. Wait, I think no. The distributive laws hold. Then all of what we constructed over any period of time in our studies of linear algebra, so even if it's computational or proof based, we can reconstruct all of um, all of the stuff here or of the stuff we already did in the terms of abstract fields and abstract vector spaces. Now, yeah. Um, there is also of course isomorphisms of fields that is mentioned here. But like before that, Professor Benedict Gross apparently in my notes goes over that there are subspaces of the vector spaces that can be constructed in the abstract on the over the abstract fields. Uh, we have we can actually make the vector space zero, the zero vector, the vector space for any field. There is the vector space f. There is a vector space fn, and we see that each one of those is a subfield of the other. The real vector is a subfield of f. Is a subfield of fn, and there is of course other vector spaces, and mm, if we can say a team that takes the transformation T that takes from V to W vector spaces, V is a vector space and W is a vector space. It's actually a homomorphism uh, of vector spaces. Yeah, homomorphism of vector spaces. That actually have addition in it. TV plus that equals TV plus dw. And there's a scalar multiplication. TV equal C dot TV. Now, if T was bijective maps, then it would be named isomorphism. That is the linear transformations. Any homomorphism between two fields, two vector spaces, two over fields is called linear transformation. Actually, the study of linear algebra is all about linear transformations. And we also know we will need that in the section 4.1. We know that the kernel of just like normal group theory stuff we actually worked. We know that the kernel of T is the set V where TV equal to the and the image of T is TV where V is in V. That's subspace of V and that's subspace of W. Yes. I yeah. I think that concludes section 4.2. Yeah. Uh, Now we will start. If no one has any questions, I will look at the chat. Yeah, yeah. I'm sorry for if my cam resolutions is a bit wonky because Egypt's network is not the very best. So if there is no other questions regarding abstract vector spaces or abstract fields, I would like to continue. Okay. I don't see anyone typing. Okay. So we will start. Infinite dimensional spaces. There are actually some vector spaces that are kind of too big to be spanned by any finite set of vectors. These are called infinite dimensional. I didn't see Professor Benedict Gross actually discussing these two sections. So I will just explain it how the book has explained it. Um, the you see, there's the most obvious infinite dimensional space is R infinite, where an A, vector A, and yeah, vector A R infinite is is written in this way: A1, A2, A3, and so on, without an end. That's actually uh, an infinite dimensional space, but like infinite dimensional spaces are mostly used in analysis, but like we will not discuss it as much in our discussion of abstract algebra. But like it worth the mentioning of it because there's actually some pretty good theorems that I want to go through over. Uh, the book mentions examples uh, of finite dimension, infinite dimensional spaces. Like the book mentions that convergence sequences is an infinite dimensional space, bounded sequences, absolute convergence sequences, and sequences with finitely many non-zero terms. Yeah, this one is. I won't write this one. No. Uh, Z. Uh, should I use Z for? Uh, uh, actually, forget it. Yeah. Let's just use Z. V is A and R infinite, where an equals 0 for all but finitely many n. That's an infinite dimension space, but it has actually uh, quite interesting fact about it. Now, but before we state that fact, a set like I just want you to think of the questions. Yeah, polynomials are infinite dimensional spaces. Yes, but like I want to actually uh, to think about the questions that I will ask. Is it possible that an infinite set of vectors span an infinite dimensional space? And can this happen? No, an infinite amount of vectors. Would it span an infinite dimensional vector space? The answer is actually easy if you are familiar with series. Oh, it seems actually the answer is no. No, it cannot. Because there are some series that diverges, not converges. So we wouldn't know what is the linear combination that we assign to get our any vector for for in our space. But actually, sometimes it's as another question. Can a finite set of vector spaces span an infinite dimensional vector space? You see, the difference between the questions that I first asked and now is two distinct points. The first point is that I'm asking about a finite set, and the second point that I'm now asking for some any arbitrary field. Like, if there's any one field that can infinite dimensional space that can be spanned by finite set of vectors, the answer of the question would be yes. Maybe actually it's yes. Let's see how would that be. I wrote here this infinite dimensional, infinite dimensional um, space because it actually has very very important fact about it. You see, let's say the set of vector can you see my camera? Yeah. Okay, uh, uh, yeah, yeah. Yes, I think you can see. Where it has the set EI, where EI equals 0, 0, 1 in the ice place, and then 0 to infinity. You see, this here is actually spanned by finite numbers of this set of vectors. I only need n vectors, n vectors, n here. You see, for all the space here is said that an is equal to 0 for all n but finitely many n. Let's say that n was 1. So I only need one vector here to span the entire space. If n was 2, I would need 2. If n was infinitely, I not infinite. If n was like arbitrarily large, I can still get a finite number of vectors in S to span that infinite field. Kirby asked again, could you just have one infinite by infinite vector? I don't understand your question. You can open the mic and ask it.
Like essentially, you said that when n equals 1, you can just have like one vector. It's like infinite,
Yeah,
right? So
yeah.
would that one vector just be like an infinite by like have infinite rows and infinite columns?
It's not a matrix,
Oh, true.
but yeah, but like the vector, yes, it would have infinite elements. Infinite elements. We're not talking about dimension. We're talking about the finite number of vectors, and would they span the field? Yeah. Uh, the important, the fun, the fun part about infinite dimensional spaces is that in the end of the section, I actually want. Uh, let's actually. I will screen share. Wait? Kirby has a question. Does the countability of the infinite matter? I don't think so. Yeah. The proposition here, the first proposition, the fun proposition. Let V be a finite dimensional, and let S be any set which spans V. Then set contains a finite subset which spans V. The proof here is by assumption. There's some finite set W1 and to Wm which spans V. You see, as V is a finite dimensional, we know that every finite dimensional space has bases. So we know that there exists at least one base W1 to Wm which spans V. Each W1 is a linear combination of finitely many elements of S because S also spans V. Since span V equals V, span S equals V. So when we express the vectors W1 to Wm's in terms of the vectors in S, like H1 is a linear combination of some elements in S. So if I replaced each vector for Wi to Wm in terms of the elements in S, we only need to use finitely many of its elements because each each vector has finite span is a linear combination of finitely many elements of S, and the set itself in W1 to Wn is finite. And to W1 to Wm is in the span of V dash, then C dash is also spanning the entire field. Now there's another fun proposition here. Let V be a finite dimensional vector space. It says that every set which spans V contains a finite basis. Every the proof of that um, it's basically the proposition 5.6. Now, every linear independent set is finite and therefore extend to finite bases. Uh, the proof of it, the proof for that, like you see, if we assume if L was infinite, it would contradict. Yeah, uh, I will get back to my writing board, if I can call it that. Yeah. Uh, yeah. The proposition says let V be a finite dimensional finite dimensional vector space. Yeah, then beam, then every linear independent set L is finite and or and to a finite basis. That's an easy proof by contradiction because if L was infinite, if L was infinite, then it would contradict the fact that V is a finite dimensional vector space. And we proved in our past lectures that any set of linear independent vectors can be extended to a finite basis, because we know that also uh, each every now we go to the last y finite basis, because it's finite dimensional vector space. Now that actually combined with the propositions that we had just read gives us the last conclusion that every basis is finite. I can prove that with with the, with the theorems that we actually discussed before of the extension, and like mm, every set of bases I can take some vectors out of it and make a linear independent set, and like it's trivial at this point. Uh, so the the three that's the three conclusions that we made, going back to the screen share, this these conclusions that we made here are the main purpose that why we are talking about infinite dimensional space here. That concludes the section for infinite dimensional space. A good small section. Any questions about it before going into the directed sums? We see that in the author here says, let V be a vector space and let W1 dot Wn be subspaces of V. Amount shows the treatment of linear independence and span of vectors has analogs for subspaces. Mm, you, as I'm all what I've done in constructing before, in constructing a linear independent set and the bases and the span and so on and so forth, have analogs here in the notion of subspaces. We know that any vector can be written as a sum here, as a sum of another vectors wi plus dot plus wn, where wi is a vector in the subspace wi. This, as I said, is trivial considering the stuff that we actually went through before. Now, the set of all such vectors that is called the sum of the subspaces or the span of the subspaces. That's the first analogous stuff, analogous thing that we are going to discuss here is the span. You see, if I added uh, all the subspaces in the way that I denoted the vector v as a linear combination of wi's, I can add the subspaces, all of it, like as defined here. The addition of subspaces or the span of subspaces are the set of all vectors v's where each v can be described as an as a linear combination of wi's. The sum is also a subspace of V, analogous to the span of any set of vectors. Clearly, of course, it's the smallest subspace containing subspace W1 dot till Wn. Now, the next thing that we are going to discuss are the subspaces. When are the subspaces called independent? They are the subspaces W to Wn are called independent if there is no sum W1 to Wn was Wi belongs to Wi. I think they forgot an I here. Is zero, except for the trivial sum where in which Wi is zero for all I. In other words, the spaces are independent if W1 by the plus dot plus Wn equals 0 and Wi belongs to Wi capital implies that W small I equals 0 for all I. In case the span is the whole space and the subspaces are independent, we say that V is the directed sum of the subspaces W1 till Wn, and we write the directed sum with this funky little symbol here. If we say that V is the directed sum of W1 till Wn, if V equals the span of W1 till Wn, and if one W1 till Wn are independent. This is equivalent to saying that every vector V can be written in the form here. It can be written as a linear combination of W1 to Wn, and so on and so forth. So and it's the only way, it's a unique way. So if W1 till Wn are independent subspaces of a vector space V, and if W plus Wi plus dot plus Wn is their sum, then in fact U is their directed sum. Mm, you know, I think you get the idea of the directed sum here. There's two propositions, not as fun as the propositions that we talked about before. That a single subspace is, of course, independent. That's trivial. The propositions are trivial, but like I will post them. I will post them now in the problem form of Arten. A single subspace is like, by the definition, is independent. Two subspaces are independent if and only if their intersection is zero. And the second proposition says if W1 to Wn are subspaces of a finite dimensional vector space V, and let Bi is a basis of Wi, the ordered set obtained by listing the bases P1 to Pn is in order is a basis for V if and only if V is the directed sum of W1 until Wn, and also the dimension of the span of the vectors W1 to Wn is less than or equal the dimension of each subspace added with equality if and only if the subspaces are independent. I hope you can understand at least the proposition, what the proposition says. If not, you already know how would you prove them. Are there any problems with these propositions? Yeah, I don't think so. Great. Then there is a corollary that let W be a subspace of a finite dimensional vector space V. There's another subspace W dash such that V equals the directed sum. V is the directed sum of W and W dash. I think you should also have a quite clear uh, image of what it says here, because let W1 to WT be a basis. The proof here, let W1 to WD be a basis for W, extend to a basis for V. We talked about the extension of basis. Then the span of V1, the span, look, the span of the extension is the span of the required subspace W dash, and V is, of course, like R is their directed sum. There's an example here that you can check in the book. Now, the last proposition, the last fun proposition in the chapter is this is where I want to talk about, like, take a moment to appreciate its beautifulness. Let W1 and W2 be subspaces of a finite dimensional vector space V. Then the dimension plus of W1 plus the dimension of W2 equals the dimension of their intersection plus the dimension of their addition. You see, if you prove that proposition, this part here in proposition 6.6 could be even more trivial. And with equality, if and only if the spaces are independent, you see, their intersection, would be zero, and the dimension would be zero. So, the dimension of W1 and plus W2 would be right away equal the dimension of their sum, or their span. If I'm talking too fast, please stop me. But like, as Benedict Gross said, I tend to go faster and faster. So if I'm too fast for anyone's understanding, please stop me right away. Now the proof. Note that first that the intersection of two subspaces is again a subspace. Choose the basis W1 to WR for the space W1 intersecting W2, where R is the dimension of W1 and W2 intersecting W2. This is a linearly independent set, and it is, of course, in one because it's intersection. Hence, we can extend it to a basis of W1 by by this equation here, and where m is the dimension of W1. Similarly, we can extend it for W2 by this equation here. Now, where n is also the dimension of W2. The proposition will follow if we show that the set W1 to U1 to UR with the extension of x1 to the x m minus r and the extension of y1 to y n minus r is the basis of y plus 2. The assertion here has two parts. First, that's the vectors, and this equation here, 6.12, span the span and the sum of W1 plus W2. For any vector in W1 and W2 is the sum of some W1 and some W2, where is what W1 is belongs to W capital 1, and we can write W1 as a linear combination of 6 to dot 10 here. We know we extended the basis of the intersection to be a basis of W1. Now, and we can write W2 as a linear combination of 6.11.2. Yeah. Can you zoom in a little? Yeah, of course I can. Is this good enough? Yeah, of course. Uh, I can zoom more if. Yeah, okay. Now we can write, as I said, we can write W2 as a linear combination of the equation of here. We know we extended the basis of the intersection to be a basis of W2. We can write this as a linear combination here. Next, the vectors. Collecting the terms, we find that V is a linear combination of W1 of 6 point of the equation 6.11, because you see it's a sum of W.1 and W.2. Next, the vectors in 6.6 and 0.11 are linearly independent. Then suppose that some linear combination is zero, say here, that linear combination is zero. We can abbreviate this as W plus X plus Y equals 0. W is the basis of the intersection. X is the extension to span W1, and Y is the extension to span W2. We can solve this for Y, so it will be Y equals minus W minus U minus X, which is belong to Y1, but Y it belongs to Y2. Hence, Y is in the intersection of Y of W1 and W2, and so Y is a linear combination, say U prime of U1 to UR, then minus U dash plus plus Y equals 0 is a relation among the vectors here 6.11, which are independent, so it must be the trivial relation. This shows that y equals 0, thus our original relations reduces to to u plus x. And since 6.10 here is a basis, this relation is trivial. That 0 u equals 0 and x equals 0. So the whole relation are trivial as required, so they are linearly independent and span V. So the dimension of W1 plus W2 equals the dimension of the intersection, which is R here, the base is here, plus the dimension of their addition, which we made here. Is that clear for everyone? Are there any questions?
Yep.
Yeah.
No questions.
Yeah, great then. We finished